So this question is called World Ladder, and we're getting here a list of words and a start word and a target word. And what we need to do is to find a path from the start word until the target word with the limitation that we can transfer from one word to another word by only changing one letter. Then if we're looking at this example, then we should return something like this. We're starting from tune, and then over here we're only changing the letter T. We're changing it to P. So we are here left with pun. Now changing this O to I, and we're going to point, and from point to poi by changing N to E, and so on until we get to pli. Now notice that we only change one character at each time we transferred to another word, and this is called the distance between the word. So there are many ways to solve it, but we're going to solve it using graph algorithms and neo4j. And it's going to be a complex solution because we're going to have many files, but the principles of the solutions is very simple. So at the beginning, I'm just going to go briefly over the files and going to describe what's going to be in each file, and then we're going to go deeply and see how we implemented each file. So let's take a look at our file structure. Over here, we have the input.json file, which is simply going to be the input of our problem. We have here a runner file, which is going to just run the functions in order to solve our problem. So one function is going to be the function which creates our graph database, and another function is going to be a function that will find the shortest path from one node to the other node. We have a graph.db file, which simply is going to be responsible to build our neo4j graph database. And we have a word ladder file, which simply going to have the query that solves our problem. This query over here is going to be calling Dijkstra's algorithm, and we're going to return from it the shortest path from the source node to our dest node. Here we have the Ven folder, and the Ven folder is our virtual environment. So in order to configure our virtual environment, we need to go to PyCharm Preferences, and then go to Project and then Project Interpreter. And here we can define a project interpreter. We're going to just create a new one. I already created and called it Venv. Click OK. And then after it, we can see that in our terminal, we are inside the virtual environment. Afterwards, we just need to pip install our neo4j runner. So we just write pip install python-neo. So this is the package that will help us solve this. I already have it installed. Now notice that our interpreter is using Python 3. So make sure that you have Python 3 and above and not Python 2, because those are old versions which are not supported. And one last thing that we need to configure is our runner function. So we can just edit the configuration and we can put the path to our runner file. So this is our runner.py. We're just going to put the path, and then we're going to apply it, and we're going to make sure that it's using our interpreter that we installed, the python-neo, and then we would be able to run our solution. So here we have the input file, which is just going to be a JSON file. And then we're going to parse this file into a graph. We're going to take this file and we're going to build a graph from it. So we're going to build a graph where each node is going to be a word. So for example, we're going to have a node for pun, a node for pli, and so on and so on. And we will connect two words to each other, those nodes, only if the distance between them is only one character. After we've done that, all we need to do is just run Dijkstra on our graph from our start node to our target node, and Dijkstra's algorithm will return us the shortest path. Of course, we will put a weight on the edge between those nodes, and we're going to put an arbitrary weight of 1. And then Dijkstra will find us the path from start to target, which has the minimum weight. And because we put the weight to be 1, then it will just basically says what is the shortest path from start to target. Let's take a look on our runner. It's basically what's going to run our entire solution. So first we want to build our graph. So we'll create a function that's called initialize neo4j db By the way, neo4j is a graph database that we're going to use, and we'll soon see how to do it. So after we've done that, we can say we have a graph. We want to find the shortest path between those words. And we will see how to do it also. And that's going to be a neo4j query, which is already built in. And afterwards, we'll just print the results. So let's just take a quick look on our graph that we created. Again, we're not talking about the implementation, just about the general idea. So from the list of words, we are creating this graph. You can see here each word is a node, and it has an edge to another word if the distance between them is 1. And again, you see we have here a property of cost, which is going to be the weight of the edge, which is 1. So for example, from pli to pli, we can see easily that by changing A to E, we can switch between the nodes. So we get this for the entire words of our input. So that's how we build the graph. So what we do now is simply start from our starting word, for example this one, and then just run the Dijkstra's algorithm. And because neo4j is a graph-based database, we get that for free. We can just use a library function which would run us Dijkstra's algorithm with it's already implemented, and we don't have to do anything but to call this function. So you can see if we will run our solution, we will get exactly the output we want. So now that after we talked about runner.py, which simply runs our functions, let's start talking about each component. So first, let's see how we build the graph with neo4j. So now we're looking at the file graphdb.py, and this file is going to be responsible to creating our graph. So at the beginning, I'm importing JSON because I'm going to use this when I parse our JSON input, and we need to use py2neo, which is the Python extension to help us run neo4j. So in order to support this, we need to have neo4j installed. So if I were to go to my interpreter, I'm going to see that I have already installed py2neo. But if you want to install it yourself, what you want to do, okay, and this is only for Mac or Linux environment, you first want to create your virtual environment, which I created it before, and we want to activate it. So we'll just simply write source venv bin activate. This activates our virtual environment, and now we simply need to install with pip py2neo. But I already have it installed, so I don't need to install it again. If you won't have this, it will install you py2neo. So here is just a simple constant. So here is the password for our neo4j database. So if I go to the neo4j console, and I will look at the settings, then I can see that if I go to the administration section, I can change a password. So the password I'm going to type here is supposed to match the password I write over here. So this is the password in order to make everything be configured. Now, we have here a few functions. So let's take a look from the main function. We have here a main function which is called initializeDB. And what it does, it simply opens our JSON input file, which is over here, and loads its data. Now we're searching all the words in our JSON file, and we're putting it in a variable called words. So if I'll just open the input JSON, we're simply accessing this field over here, and words will be just this array or list of words. Now we're initializing a graph object. So this graph is going to represent our neo4j graph. And notice in the constructor, I'm using password field and sending it the password which I configured in my neo4j. And right over here, we're just opening a connection to our graph. So we're using the begin function. And if you want to get more information about the neo4j driver for Python, you're most welcome to go to the documentation, and you have all the information there. But this is not a neo4j course, and we're not talking about it now. So this line over here just opens a connection to our graph. And now we're going to create the nodes, and we're going to create the relationships. And this line over here will actually execute all the stuff that we built and would make our database be stored with all the nodes and edges we created. And eventually, of course, we want to return the graph. So let's take a look now on the create nodes function. So it receives words in a transaction. So this function is very simple. We're simply going to iterate over the words. We're simply going to create a node object, which is going to be of type word, and we're going to put a value there of the string we're creating. So for example, for the word hi, we're going to have a node of type word, which is going to have the value hi. So after we created our nodes, it's time to create the relationship. We need to create the edges between those nodes. I remind you that we want to create an edge between two words, for example, hi and he, only if we can go from one word by changing one letter to the other. So over here in this example, we change I to E. So this we're going to call edit distance, and it's a very famous problem, and it has a very common implementation. And I'm not going through the implementation of the edit distance, but we need to check if the edit distance is equals to 1. So right over here you also have the edit distance function. You can go through this implementation, and we only want words that their edit distance from each other is 1. So we're going to go through all the couples of the words, all combinations, and only if the edit distance is 1, we're going to create an edge. So we want to create a source node and a dest node, because we're going to have an edge from the source to the dest, and we're going to create those nodes. And if they already exist, we don't want to create them, we want to use them. So we'll use the merge function, which basically creates an object of node if it doesn't exist, and if it does exist, it doesn't create. And then we want to create a relationship between our source node and dest node. We're going to call this relationship edit distance, and we're going to give it an attribute of cost with the value 1. Okay, this is going to be the weight of this edge. And then we just want to use the merge function and also for the relationship. So after we'll initiate everything, we'll have all the relationships ready. So again, if I wrap everything up, we first create our graph, which is initialized to have nothing. We then create the nodes and then create the relationships, and then we save the data to be persistent in our neo4j graph. And we can see the graph that we built over here. In this example, it would build us this graph. So we have each node is a word, and we have an edit distance true edge only if the edit distance is 1. And we have also the attribute of 1, so we can run Dijkstra's algorithm. So now let's go to our final function, which is actually the function that solves our solution. So it's going to be word ladder. So this function, it receives our graph, our source, and our target, and it simply asks neo4j to run a query that we want, which the query is going to simply run Dijkstra. So let's take a close look. Now this is not a neo4j course, but we can simply see what's happening over here, and we can understand most of it. So right over here we simply want to first find the node source and the node target. So we'll find the node. So this match will cause that. So this match clause will find us the source node and target node. We can see we're looking for a start node of type word, which is value equals to the source parameter. We can do that by using the APOC library. We also need to configure our database to have graph algorithms. So we can do so by going to our neo4j graph project. So if we'll go to the settings section over here in the manage section, we'll go to settings. We simply need to paste those two lines in order to use Dijkstra's algorithm, because it doesn't come built in. After we pasted those lines over here in the settings sections, we simply need to click the restart database, which will load all the changes to our database, and then we can use the Dijkstra's algorithm. And APOC means awesome procedures on Cypher, and Cypher is the query language of neo4j. We're going to use the algo section in that library, and we're going to use the Dijkstra's function. And this function needs to receive the parameters, the start node, the end node, what are edges we want to iterate over, and what is our weight function. So our weight function is called cost. It's going to be our attribute. And what's the default value? So we set the default value for 1, but we don't actually really need it. And then we're simply going to return the path we find. And a Dijkstra's algorithm is going to return us the lightest path. And we talked already that the lightest path is going to be the shortest path in this case, because each weight of each edge is only equal to 1. So we're going to run this query. Okay, so we're going to run this query. And we're going to get a cursor object. And I'm not going in what is a cursor, but basically it will hold our result. So after it, we'll just parse our cursor object and we'll get our results. Now notice one thing over here, that if we were to run this query in our neo4j browser, so if we were simply to run our query on the neo4j browser, you can see here I switched the value to tune and the value here to plea, so it won't have those parameters from our function call. And if we run this query, we can see that we get the result that we want. We can see we get from poon until we go to plea. So we get the entire path. Now notice over here we're getting a warning, and this warning says that we're building a Cartesian product. So it's basically saying that our query may suffer from performance issues because we are having a Cartesian product, and we can get rid of this warning message if we switch the first line with this line. So I'm not going into the neo4j cipher query language, but we can do it more efficiently and it would return us everything and much faster. If you want, you can check out my neo4j course. I explain a lot about neo4j and the cipher query language and how to configure everything in that course. So this solution just want to show you that you can use other technologies in order to solve the problem. So it's not a neo4j course, but it's very nice to know that you can do it with other technologies.
So what's going to be the runtime complexity of our algorithm? Well, first we need to iterate through all the pairs of our words. So this will cost us big O of n squared, where n is the number of words. Then for each couple, for each pair of words, we need to iterate through the entire word to see if there is an eddy distance of 1. So this will cost us k, where k is going to be the length of the maximum word. So eventually we have n squared times k. Afterwards, running Dijkstra is linear with the number of nodes and edges, so it's still less than n squared times k. So our entire solution is going to cost us big O of n squared times k.